The topic for the discussion is organization of records and files. There are several possible ways for organizing records and files, that is, heap file organization, sequential file organization, hashing file organization. Heap file organization. In heap file organization, any record can be placed anywhere in the file where there is space for that record. There is no ordering of records. There is single file for each relation. In sequential file organization, records are stored in sequential order according to the value of a search key of that record. In hashing, a hash function is computed on some attribute of each record. The result of the hash function specifies in which block of the file the record should be placed. A separate file is used to store the records of each relation. However, in a clustering file organization, records of several different relations are stored in the same file. Let's move on to sequential file organization. A sequential file is designed for efficient processing of records in sorted order based on some search key. A search key may be any attribute or set of attributes. It need not to be the primary key or even a super key. To permit fast retrieval of records in search key order, we chain together the records by pointers. And this is shown in that figure. The pointer in each record points to the next record in search key order. This figure shows a sequential file of account records taken from the banking example that we already seen in previous topic. In this example, the records are stored in search key order using branch name as the search key. The sequential file organization allows records to be read in sorted order, but it is difficult to maintain physical sequential order as records are inserted and deleted. Since it may be costly to move many records for a single insertion or deletion, so we can manage deletion by using these pointer chains. For insertion, we have to apply some rules. We have to locate the record in the file that comes before the record to be inserted in search key order, and if there is a free record within the same block, insert the new record there. Otherwise, insert the new record in an overflow block. We already seen what is overflow block. In that case, in either case, adjust the pointer so that the chain together so as to chain together the records in search key order. If few records need to be stored in overflow block, this approach works well. However, the correspondence between the search key order and physical order may be totally lost. In such case, sequential processing will become much less efficient. At this point, the file should be reorganized. Next, the clustering file organization. In many relational database systems, store each relation in a separate file so that they can take full advantage of the file system that the OS provide. The simple implementation of a relational database system is well suited to low cost database implementations. Here, many large-scale database systems do not rely directly on the OS for file management. Instead, file is allocated to the database systems, and the database system stores all relations in this one file and manages the file. Mm, Here, a clustering file organization is illustrated in this figure. It stores related records of two or more relations in each block. Such a file organization allows us to read records that would satisfy the join condition by using one block read. One use of clustering, uh, it will enhance the processing of a particular join operation, but it results in slow processing of other type of query. So in this to locate the tuples of this relation, in this figure, we need to chain together all the records of that relation using pointers, um, so that the clustering organization can produce the significant performance in query processing also. The next topic is data dictionary storage. Um, we know that data dictionary means the place where all the information is made available in the database. A data dictionary is a crucial part of a relational database, as it provides additional information about the relationship between multiple relations in a database. Um, it helps the user to arrange data in a well organized way by preventing the redundancy. The database also needs to store information about the relations, known as a data dictionary. This includes name of the relations, name of the attributes of relations, domains and lengths of attributes, names and definitions of use, integrity constraints or key constraints, mm, and data on the system users, names of the authorized users, accounting information about the users, and possibly statistical and descriptive data, the number of tuples in each relation, method of storage used for each relation. We will also need to store information about each index on each relation, that is name of the index, name of the relation being indexed, attributes the index is on, type of index. So this information may be a miniature database. We can use the database to store data about itself, simplifying the overall structure of the system and allowing the full power of the database to be used to permit fast access to system data. The exact choice of how to represent system data using relations must be made by the system designer. One possible representation is, um, uh, this is shown here. Relation metadata, that is, this is a system catalog schema. Relation metadata is equal to relation name and number of attributes. Next, attribute metadata, attribute schema. This is attribute name, relation name, and domain type, position, length. The next one is user schema or user metadata, username, encrypted password, and the group. Next one is index metadata, index schema, index name, relation name, index type, and index attributes, and view schema, view name, and definition. So this is the possible catalog representation of um, designing a data dictionary. So this is all about data dictionary storage. Then we move on to the indexing and hashing. Mm, so indexing provides the most powerful and flexible tools for organizing files. This mechanism used to speed up access to desired data, and indexing mechanism uses search key attribute or set of attributes to look up records in a file. However, indexing has uh, has some disadvantages. Indexes take up space and time to keep them organized, and the amount of IO increases with the size of index. This problem can be minimized by direct file organization, where the address of the desired record can be found directly. No need of indexing, that is sequential search maybe. Such files are created using some hashing mechanisms. Um, there are two basic kinds of indices: ordered indices and hash indices. Ordered indices, it is based on assorted ordering of the values. Hash indices based on a uniform distribution of values across a range of buckets. The bucket to which a value is assigned is determined by a function, hash function. Then the index evaluation metrics. This techniques must be evaluated on the basis of these factors, that is access types, access time, insertion time, deletion time, and space overhead. Access types, these are the types of access that are supported efficiently, and access time, the time it takes to find a particular data item, and insertion time is a time taken to insert a new data item, and deletion time is takes to delete a time it takes to delete a data item, and the space overhead, the additional space occupied by an index structure. Next, ordered indices is, each index structure is associated with a particular search key. An ordered index stores the values of the search keys in sorted order and associates with each search key the record that contain it. So, a file may have several indices on different search keys. If the file containing the records in sequential order, a primary index is an index whose search key also defines the sequential order of the file. Primary indices are also called clustering indices. The search key of the primary index is usually the primary key. Indices whose search key specifies an order different from the sequential order of file are called secondary index or non-clustering indices. Primary index, in this files with the primary index on the search key is called index sequential file. Here we are going to see the dense and sparse indices. In this is the dense index. There are two types of ordered indices. One is dense index and sparse index. Dense index, an index record appears for every search key value in the file. In a dense primary index, the index record contains the search key value and a pointer to the first data record with that search key value. The rest of the records with the same search key value would be stored sequentially after the first record. This is the figure for dense index. Here, every search key value, an index record appears for every search key value. Then the sparse index, an index record appears for only some of the search key values. To locate a record, we find the index entry with the largest search key value, that is less than or equal to the search key value for which we are looking. It is generally faster to locate a record if we have a dense index rather than a sparse index. However, sparse indices have advantage over dense index in that they require less space and less maintenance overhead for insertion and deletions. This is the example of sparse index files. Next, we move on to secondary index. The secondary indices must be dense, with an index entry for every search key value and a pointer to every record in the file. Secondary index on a candidate key looks just like a dense primary index, except that records pointed by successive values in the index are not stored sequentially. Um, if the search key of a primary index is not a candidate key, the index points to the first record with the particular value for the search key. Since the other records can be fetched by a sequential scan of the file. It has some advantages and disadvantages. The secondary indices improve the performance of queries that use keys other than the search key of the primary index. And the disadvantages, secondary indices imposes a significant overhead on modification of the database. Next topic is multi-level indices. Indices with two or more levels are called multi-level index. Um, The problem with sparse index is the index itself may become too large for efficient processing. Uh, shall we consider a file with 100,000 records with 10 records stored in each block? If we have one index record per block, the index has 10,000 records. Index records are smaller than data records, so let us assume that 100 index records fit on a block. Thus our index occupies 100 blocks. Such large indices are stored as sequential files on disk. If an index is sufficiently small to be kept in main memory, the search time to find an entry is low. However, if the index is so large, it must be kept on disk. A search for an entry requires several disk block reads. If the index occupies B block, binary search requires as many as log 2 B blocks to be read. To deal with this problem, we use two-level index structure as in figure. To locate a record, we first use binary search on the outer index to find the record for the largest search key value less than or equal to the one that we desire. The pointer points to a block on the of the inner index. Then we scan this block until we find the record that has the largest search key value less than or equal to the one that we desire. The pointer in this record points to the block of the file that contains the record for which we are looking for. If we assume that the outer index is already in memory, then using the two levels of indexing, we have read only one index block rather than the 7 we read with binary search. If our file is maybe extremely large, even the outer index may grow too large to fit in main memory. In this case, we can create another level of index. Searching for records with a multi-level index requires significantly few I/O operations than binary search. So this is the example of multi-level indexing. Thank you.